let us get started. So this week, of course, we're going to be having our first exam. Looks like it'll be on Friday. So the plan is today we'll do a couple of examples, finishing up the problems on radiation. Wednesday, we'll have our exam review. So we'll meet normal class time, and I'll go over all the topics we've discussed over the semester, which, what are the topics that are going to be on the test, what to expect. Of course, if you had me last semester for Physics 1, then you already have an idea of what my tests look like, how they're run, and things like that. And if you didn't have me, then I'll do my best to kind of explain what to expect. So, you go into it not as fearful of the unknown as is usual. And so Wednesday would be the exam review. And then Friday, I'll post the test in the morning. You take whatever time you want to download it, work it out, submit it back, and the deadline will be Friday by midnight, 11:59 p.m. So you'll have plenty of time to work on it. It's not working on it on the website, on Canvas itself. It's just like the homework problems. You download the PDF file, and then you handwrite the solutions as usual, and then submit it back. That way, if you want to work on it in the morning or in the afternoon, whenever you're free, if you want to come back to it after a while, all of that is fine. So that's kind of the plan for this week. Of course, after the test, next week we'll start into the next big topic. Also of note, so first of all, exam 1, Friday. Also of note, of course, is the homework problem for radiation is posted on Canvas. So don't forget to work on that as well, especially as you're studying. You may as well work the problem out if you haven't already done so, because that problem is a good representation of the type of radiation problem you'll see on the test. So don't forget about the homework problem as you're studying for the test. Let's see. So let's go over radiation. What was it we did last time? Well, of course, we did some examples on the basic form of the radiation equation, which is that the power, or the heat transfer rate, the power radiated by an object of a certain temperature, is given by a constant, sigma, that's Stefan Boltzmann's constant, epsilon, which is called the emissivity, and this basically is how good does this particular material radiate. A perfect radiator, it radiates at 100% efficiency, so it would be an epsilon of 1. A 10% radiator means it's only 10% efficient, so the emissivity would be 0.1. A, that's the surface area of the object. So obviously, the bigger the object, the more places there are for radiation to come out of. And so you'll have more power radiating from a larger object, or at least an object that has more surface area, than something that's much smaller. So if you have a small steel ball or you have a large star, and they're both at the same temperature, the star will be able to radiate a lot more heat, a lot more energy than the small steel ball, even though they're at the same temperature. So that's what capital A is. And then there's the last term, which is T, the temperature to the 4th power. And we noted here that because, as was described when we first got into thermodynamics, the units appropriate for physics for temperature is Kelvin. So we're supposed to be using the Kelvin scale all this time. But we found that there's kind of a shortcut, a little trick, that says anytime you see delta T, the difference in temperature or the change in temperature, then you can actually use Celsius instead of Kelvin and still get the same answer. It was a trick. But now we see we have an equation sitting in front of us where we don't have delta T anymore. This is straight up, what is the temperature? And so because of that, we have to be careful to use Kelvin as our units. And if you don't remember how to convert Kelvin, the temperature in Kelvin is the temperature in Celsius plus 273. Very easy conversion. And so that's what we had last time. And from here, of course, there's plenty of different types of questions can be asked. What's the power radiated? Or if I wait 2 days, how much energy will come out? Or what must be the temperature such that this star radiates this much power? Obviously, you take this equation, you solve for whichever variable it is the question's asking about, and you plug your numbers in. But we then went further and said, this is actually a special case. This is not the general equation. This is a special case when the object we're talking about, let's say, is sitting out in space. Because there's a significant difference in how the energy wants to be transferred if you have an object in an environment that's nearly the same temperature. So, you have a hot pot and it's in an oven that's also hot. Well, since they're at nearly the same temperature, the pot's not going to radiate as much energy as it would if that hot pot was actually in a refrigerator. Whenever you have a large difference in temperatures between one object and its environment, or one object and another object, then there's a real big pull to transfer that energy quickly. And of course, we saw that with conduction. With heat conduction, if you have, your room temperature hand touches the stove, which is very hot, that energy really transfers from the stove to your hand very quickly, because it's just like if you think about in any other thing, if you have a very dry area and then a very wet area and you put them together, you let them touch, the moisture really gets pulled into the dry area to try to balance everything. Well, of course, the same goes for heat. And so the same, of course, would go for radiation as well. If I place this object in a warm environment, it won't radiate as well as it would have if it's in a cold environment. And so this equation assumes that the object is placed in an environment that's at 0 temperature. Something like a star out in outer space. That's a good approximation. But the true equation takes into account that in real life, whenever you have an object that can radiate, it's in some area, it's in some environment, which is at its own temperature. And that temperature for the environment may be cold, it may be hot, but whatever it is, we should certainly consider it. And so the true equation is very similar. The power radiated is sigma epsilon A, but now we have to worry about not only the temperature of the object which is radiating, but also the temperature of its environment, where you've placed that object. And what we found was the equation was the temperature of the object to the 4th power minus the temperature of its environment to the 4th power. Okay, so that's the real equation. And the one above it, the one we started with, the simpler version, is just a special case where we assume the temperature of the environment to be 0. And so a great question is, well, how do I know which one of these equations to use? If I'm given a problem on my test and you're not here to explain to me which equation I'm supposed to use, how am I supposed to figure it out? And thankfully, the answer to that question is very simple. If the question tells you about the temperature of the environment, then you use the second equation. Whereas if the equation only tells you about the temperature of the object and doesn't say anything about its surroundings, then you use the first equation. And that's all there is to it. If you see that your problem tells you this object's at this temperature and you place it in this space, which is at that temperature, then certainly you have two temperatures sitting there. You're going to use the second equation. Versus if you look back at the examples we did last time, we basically had, what's the power radiated by a star of this temperature and this size? And I don't say anything about the temperature of its environment. And then lastly, another thing to consider, a question that could be brought up is, well, now with this more general equation, it looks like you have something like a change in temperature now. It looks like delta T, T to the fourth minus T to the fourth. It looks like delta T. So if it is delta T, do I still have to use Kelvin or can I use Celsius again? Unfortunately, this is not delta T. It is a change in something, but it's not a change in the temperature. It's a change in the temperature raised to the fourth power. And those are not the same things. In fact, I think last time I went through and proved that they're not using numbers. But just note that no matter which of these two equations you use, you have to use Kelvin. Do not use Celsius. So if you see Celsius in the problem, first step you're going to be doing is converting that to Kelvin. Then you use the Kelvin numbers to actually get the answer. Okay, so don't be fooled by the fact that this looks very similar to a delta T. It's not. Delta T would be, delta T looks like this. Temperature 1 minus temperature 2. So they're similar, but this is the change in the actual temperature. Whereas our equation is the temperature or the change in the fourth power of our temperatures. And that's a completely different story. So Kelvin for both, no matter what. Don't use Celsius when you're talking about radiation. All right, so before I work any examples, are there any particular questions you have either on this modification or the original equation we've been talking about?
For the second equation, did you say assume the environment is zero or the object?
Yeah, what I said was this is the big equation. However, what we did first was a simple version, which is that equation. And how do I get that equation? I got it by assuming the environment temperature is zero. So if you assume the environment temperature is zero, then all you have is the first equation. They're the same thing. However, you don't always assume that. You only assume it if, of course, the problem doesn't tell you the environment's temperature. But for a general question, when you're reading it, the question may tell you what the temperature of the environment is. You may have something like you have a steel ball whose radius is 25 centimeters and is at 500 degrees Celsius. You place it in a refrigerator whose temperature is 5 degrees Celsius. Well, there I tell you the environment's temperature is 5 degrees Celsius. Thus, you use the equation that's in the box. So I was just saying, how do we get back to the first equation we learned from this version of the equation? And the way you do it is by assuming the temperature of the environment zero, which some questions you're allowed to do. But those are special cases. That's, like I said, a star out in outer space or something like that. So don't always assume it's zero. Only let it be zero when the question allows it to be zero. If the question gives you a temperature for the environment, then you have to use it, of course. Okay, so is that more clear?
Yes, thank you. And you said we convert to Kelvin for both of them?
Yeah, no matter what, for radiation, either one of these two equations, you have to use Kelvin. Conduction and calorimetry, which we did before, had delta T sitting there. And so then we could use Celsius if we want. Of course, you don't have to use Celsius for any of them. You could use Kelvin every single time and always convert. That's good, actually. That's the way a physicist is supposed to do it. But of course, we like our shortcuts. We want to do as little work as possible. And so we usually try to avoid converting to Kelvin if we can. Radiation, you can't. Either one of these two equations, you must be in Kelvin. And of course, that goes further when you talk about the area. Don't forget, when we discuss the area, we also need the correct units for area. And that is when we're given the radius of the sphere or the size of a cube or whatever, we have to be using meters. And of course, I was grading the previous homework. Shoot. Someone had told me a while ago to make sure y'all can see grades. For whatever reason, Canvas doesn't automatically allow students to see grades, apparently. But over the weekend, I graded more of the homeworks. And I saw some problems where people forgot to convert, whether it was the thickness of the wall was given as 20 centimeters and you use 20, or cm delta t, I told you it's 150 grams, but you have to convert it to kilograms. So I saw a few instances where people didn't convert to the correct units. Did everything else right, but unfortunately got the wrong answer because the units were wrong in their calculation. So just as a big warning, be very careful when working these problems, given the numbers in the question, that before you even think about using an equation or which equation am I going to do or any of that stuff, look at the units given in the problem. If they're not meters, if they're not kilograms, if they're not Kelvin, things like that, then convert them, or seconds for time. If you're given days, you got to convert days to seconds. If you're given grams, grams need to be in kilograms, centimeters need to be in meters, and so on. So for all equations, for all of physics, and of course, if you're in chemistry, you're in biology, whatever, and there are calculations you have to do for those topics or those subjects, they all require the correct units, no matter what science you're in. So always make sure that the units you're using are the ones that you're supposed to be using, not necessarily the ones given in the question. So here, for this type of problem, Kelvin for temperature, area needs to be in square meters. In calorimetry, you need kilograms for the mass, and Kelvin or Celsius for the temperature, and so on. So that's another thing to be very careful of, because the last thing you want is to go through the trouble and work all these problems out on your test correctly, but then get points taken off here and there because the units were wrong. So make sure you convert first all the units. And then once you have the units correct, now start thinking about the problem, which equation should I use, and so on and so forth. All right, any other questions on the theory before I do an example? All right, well, let's try an example then. So what you're going to find is the example for this, the more complicated, let's call it, radiation problems are very similar to the original ones we did. You'll have something like, given a solid steel ball whose radius is 10 centimeters, which is at, let's say, 650 degrees Celsius, comma, you decide to place the ball in an oven currently at 300 degrees Celsius. If the emissivity of the steel is 70%, calculate the power radiated by the ball. And how much energy will be transferred in 1 hour. All right, so there's our question. Well, what we have is radiation. Of course, we actually have the word radiated in the problem, so that's a big clue. And we have emissivity in the problem, so that's another clue that we're talking about radiation and not conduction or something like that. Another thing I know is that I'm told the temperature of the object and I'm told the temperature of its environment. Okay, I have a steel ball, which is at one temperature, and I place it in an environment, which is at some other temperature. So that tells me immediately I'm using the equation Q over T is sigma epsilon A T object to the fourth power minus T environment to the fourth power. What else do I see? Well, I see centimeters sitting here for the radius, and that's bad. So first thing I'm going to do is I'm going to say, let's convert the radius from 10 centimeters. That's going to be 0.1 meters. I also see degrees Celsius for the temperatures, and I know Celsius is bad units for radiation, so I'm going to convert them as well. Temperature of the object is going to be 650 plus 273, right? That's how we convert from Celsius to Kelvin. We just add 273 to the number. And so we get 923 Kelvin for the object. And for the environment, we have to do the same thing because he's also at Celsius. So 300, we add 273 to that. And we get 573 Kelvin for him. Lastly, I see hours sitting there for time. And I know that the units of time should be in seconds. So I'm going to convert the time units from 1 hour. How many seconds is in 1 hour? Well, there's 60 seconds in 1 minute, 60 minutes in 1 hour. So 60 times 60 is 3,600 seconds in 1 hour. And so there we go. I now have in my question, I know which equation I'm going to use. All the units in my problem, which were bad units, I've now converted to the correct units. And so at this point, it's nothing more than a matter of plugging numbers into this equation to get an answer.
What about the emissivity when you
Emissivity, yeah.
percent?
Yeah. So I didn't convert it because it's not really converting. 70% means 0.7. But yeah, you're right. 70%, I'm not going to plug it into 70. Definitely not. That's going to be 0.7. Very good.
You said it's always going to be no more than 1, right?
That's right. So 100% means 1, 0 means 0, and everything in between is, 0.1, 0.05, whatever it happens to be.
Okay.
Yeah, very good. Perfect. All righty. So at this point, let's plug the numbers in. Part A asked me to find the power radiated. And I know that power radiated means Q over T. So I just plug the numbers into this equation. Sigma, that's the Stefan Boltzmann's constant. This will be a number given on the test. So you don't have to memorize it, but it's not so bad. It's 5.67 times 10 to the minus 8. Emissivity, 0.7 for 70%. Area, well, what do I know? This is a sphere. And I know the surface area of a sphere is given by the equation 4 pi times the radius, which I know is 0.1 squared. Okay, so that's the equation for the area. Now, of course, this is something you could do on the side. You don't have to plug it in, as an equation inside of an equation. You could on the side say, calculate the area and do 4 pi times 0.1 squared and get a number. And then you just plug the number in here. But I'm kind of lazy. I'm just plugging it into the equation like this. And then lastly, temperature of the object to the 4th power. Well, that's 923 Kelvin to the 4th power minus the environment, which is 573 to the 4th power. And there we go. There's my equation. At this point, it's just a matter of plugging this into my calculator to get an answer. Now, you have to be careful how you plug it into calculator, of course. A lot of times people get a wrong answer because, how they use their calculator is not correct. The calculator thought you wanted to do one thing and you thought you were doing something else. So just take your time with it. When I'm looking at this and I see that it's kind of a complicated mess of things, I do one thing at a time. So I'll leave these first things alone because they're fine. Really, the complicated stuff is this guy right here, the area, and this stuff here because there's the 4th power sitting there. So we leave this alone for now. 4 times 10 to the minus 8 times 0.7. All right, now this, the area. Let me go ahead and plug that in. 0.1 squared times 4 pi. And I get that this number is 0.1257. Okay, I'm keeping a lot of decimal places because if I don't, the rounding can make the answer off of what it should be. So I just kept 4 places here because I know in my answer, I'm probably only going to keep 2 or 3. So if I keep 4 in the problem, I should be, pretty good. All right, what about this stuff? Well, 923 raised to the 4th power minus 573 raised to the 4th power. And all of that stuff in the parentheses is 6.1798 times 10 to the 11th. Okay. Now, we'll just multiply everything through. So I have 6.1798 times 10 to the 11th times 0.1257 times 0.7 times 5.67 raised to the minus 8. And at the end of the day, I get an answer of 3083.14. And that is power, Q over T, energy per time. So you could either use, if you want to write the units, joules per second, or the fancy is watts. All right, are there any questions about this calculation? Hopefully you tried it yourself using your calculator and you got the same answer. If you didn't get the same answer, make sure that when you're plugging things into the calculator, you just plug them in one at a time, because I've definitely found in my experience with students and even myself that if you try to plug everything in all at once in a big equation, sometimes the order of operations go crazy in the calculator. And the 4th power acts on things you don't want it to act on, or it divides things you're trying to multiply and all sorts of weird stuff. So that's why I do one thing at a time. I do, the 0.1257 times 0.7, and I get an answer. I push enter, and I now have an answer. And then I take that answer and I multiply by the next term, and I get an answer. And then I take that answer and I multiply by the next term. So I do one thing at a time. It's not efficient. And in fact, I've had plenty of professors who have mandated we plug everything in all at once to the calculator because we should be able to do it, which is fine. But I don't care about that. I don't care if you're a master calculator user. All I care about is you can use the calculator to get the answer you need. And if it means you take one step at a time instead of plugging everything in at once, then do it that way. That's how I do it. Now, this is only part A. Of course, there's another part to this question if we remember. Part B says, how much energy will be transferred in 1 hour? Well, that's telling me the thing I'm looking for is energy, which is Q. And I'm told I'm going to look for Q given I know the time, 1 hour, T. So what I'm going to say is, look, we have Q over T. That is 3083.14. But I don't want Q over T, I just want Q. So I move the T over to the other side. And now I have an equation for Q. It's 3083.14 times T. And of course, I know what T is. It's 3,600 seconds. So 3083.14 times 3,600. And I get long number. Now, in my class, you could either do the scientific notation or you could write the number out, unless it's super crazy. So the answer I get in my calculator is 110,99296.88. You can leave it like that. Or if you remember how to do scientific notation, we're going to move the decimal over 1, 2, 3, 4, 5, 6, 7. So it's 1.109 times 10 to the 7th joules. Okay. Either way, I'll accept both on a test. But of course, if you're in science, then generally speaking, you're expected to plug everything in scientific notation, just because it's neater and you don't have this long list of numbers all over the place. But there we go. Given we now calculated the power, which is defined as Q over T, and we want to know Q, how much energy is transferred, we solve for Q, bringing the T over to the other side, plug in how much time we're talking about, in this case, 3,600 seconds, and we can get the amount of energy transferred by this object through radiation in that amount of time. So any questions about this part? All right, well, that's good. It's either good or everybody's taking a nap or watching TV or something, which may not be good, but this is all there is to the radiation stuff. We did, last class, we did the basic, which is we don't know about the environment, so we just assume it to be 0. And now we have the complex version, which, as you can see, really isn't complex. It's just adding one extra temperature into the equation. The complexity comes into the, how to plug things into your calculator. That's all there is to it. But if you could do this problem or the problem on the homework, then certainly any problem on radiation I give you on the test is going to be of this type or easier. And you can expect you'll probably have one with both temperatures, and you'll have another question with only one of the temperatures. But there's not really a lot of variety in this type of problem. Like if you remember with kinematics, well, that topic had a bunch of different types of questions that can be asked. However, here it's, you're kind of limited. You're given an object, it's going to be of a certain shape and a certain size. It's at a certain temperature, and you want to know the power. Or you know the power and you want to find the temperature. Or you know the temperature, you want to find the area. You have this one equation and that's it. You're going to use it. All right, well, that's really all I have for you today, unless, of course, you have any questions for me. So just to remind you, number 1, the homework on radiation is on Canvas, so work on it for sure. I think the deadline is Wednesday, but just check Canvas just in case it's tonight, but I'm pretty sure I made it for Wednesday. So definitely work on that. Make sure you turn it in. Friday is our first test. And just as a quick foreshadowing, it's done just like the homework problems are done. I post it onto Canvas. You download the file, work it out by hand, box your answers, submit it back to Canvas by 11:59 Friday night. And then, of course, that's all there is to it. Wednesday, our next class is going to be an exam review. So I'll come in, talk about the topics we've discussed so far, which is all thermodynamics, but basically calorimetry, conduction, and radiation. To remind you of the topics, the types of questions we had, remind you of what equations we're using, and then give you an opportunity to ask me any questions that develop as you're studying. Maybe you're working some of the problems in calorimetry, and there's something you're confused about or something you're not sure about. Then you could ask me a specific question on that unsurety, so that I can help you. So that's the plan for Wednesday. So definitely start studying, at least look over the topics and write down any questions or things you may have. That way, when I give you the chance to ask questions, we'll work on something specific that'll help you, rather than me just spouting off a bunch of general stuff you already know about. All right, so anyway, that's all I have. If you have no questions, you're free to go. And of course, if you do have a question, go ahead and ask. Stick around and ask.
Have a nice day.
All
Can you
right.
what all the tests will cover again? The radiation and
Yeah.
like,
So yeah, sure. And of course, I'll be a little more specific on Wednesday, but the topics is everything we've covered thus far in the semester, except for the math review. So we started with calorimetry. Then we went to heat conduction. And now we're on radiation. Okay, so these are the three big topics. The stuff we did for math review, the vectors, the trig, and all of that stuff, that won't be tested specifically, obviously. Of course, the algebra part is tested in your ability to actually work the equations, but these are the three topics that'll be on this particular test. So any of the practice problems, homework problems, examples we've done on these three topics, that's what you'll see for the test. Okay.
Okay, thank you so much. Have a good day.
All right, you too. Any other questions?
Yes, I had a question. I was looking at the second part of the question.
Mm-hmm.
I see how you got the answer, but I was just like, how did you calculate it? Like, when you put it in your calculator.
Yeah, so how did I get this number?
Yeah, like, because I got a number in that range, but I didn't see how you got like the
Oh,
final.
I see what's wrong. Yeah. Okay, perfect. We're slightly off of each other because the number, when I calculated this answer up here,
Mhm.
in my calculator, it's a full number. Here I rounded to 2 decimal places.
Okay.
And so what I did was I just left it in my calculator the way it was, the actual.
Okay.
And that's the number that I plugged in. I didn't actually plug this. I plugged the true, unrounded answer.
Right.
So I just left it in my calculator. And that's why the number's a little different. Though, when I'm grading, I can see, did you use the answer I got using my method, or did you use the rounded answer and it's just a little off? There's no difference to me. I won't, take off points or anything like that. I can see. Now, if the answer is off because of some other reason, because something was done incorrectly, that's a different story.
Okay.
But that's what it is. This
Okay.
answer is rounded. The answer I got in my calculator to use was the unrounded version.
Yes, sir.
All right, cool.
Thank you.
No problem.